Good morning students. In the previous video lecture we have discussed about the timing diagram and how to draw the timing diagram for various instructions of 8085. In this video lecture we will discuss about delay, what is the need for delay in a program and how to introduce or calculate a delay in the 8085 microprocessor. First we will discuss about what is a counter. Using counters, programs can specify that how many times an instruction or set of instruction is to be executed. A loop counter is set up by loading a register with a certain value. Then, using the decrement and increment instruction, the content of the registers are updated. A loop is set up with a conditional jump instruction that look backs or not depending on whether the count has reached the termination count. Here I have shown a operation of loop counter by means of a flowchart. So initially the count value is being loaded, and after that the program will be followed, and uh, the count value is being updated each and every time. If the final count is being reached, then it will terminate the program. If the final count is not being reached, it will execute the same set of instructions or lines in the program. A quite good example for this is we have seen array addition. In array addition, until the array value becomes 0, what happens? It starts picking up the number from the memory and it will add. Once the array value becomes 0, it will terminate and it will store the added result, array added result in the accumulator. Right? So such a thing is being called as a counter. Next we will see about indexing. Indexing means pointing or referring objects with sequential numbers. In a library, books are arranged according to numbers and then they are referred or sorted by numbers. This is called indexing. Similar data bytes are stored in memory location and those data bytes are referred by their memory location. Example, a list of number is stored in sequential memory location. To access this list, we need the address of first element and total number of elements in the list. We can use a register pair as index by loading this address into the pair and then incrementing it access element by the list. Next, delay. Each instruction passes through different combination of fetch, memory read and memory write cycle. Knowing the combination of cycles, we can calculate how long such an instruction would require to complete. A register is loaded with a number depending on the time delay required, and then the register is decremented until it reaches 0 by setting up a loop with a conditional jump instruction. The loop causes the delay depending upon the clock period of the system. Let us see an example for how to create this delay or how to form this loop. Right? So move immediate c comma a count value. This count value is going to be loaded by means of the user, and that makes the delay. We will see it now. Okay, move immediate c comma count. So move immediate c comma a immediate data has 7 t states. We have already seen it in the timing diagram. Move immediate c comma count has opcode fetch. Opcode fetches of 4 t states and it is being followed by means of memory read. After fetching the opcode, it has to read this count value, or it has to read the data what is being written here. So for opcode fetch, we are having 4 t states followed by means of the memory read. Right? So for reading the data, it takes 3 t states. 4 plus 3, 7 t states are being required for move immediate c comma a data. Then Decrement C is a single byte instruction, so only it has opcode fetch, so it has 4 T states. Jump on no 0 followed by means of a 16-bit address. In this, jump on no 0 has a opcode, so 4 T states followed by means of these two memories are read by means of the microprocessor. So in order to read this memory, it requires 3 plus 3 6 T states, right? So totally how many? 4 plus 6 10 T states, and the 7, I will tell why it is of 7 over here in the next slide. If the clock frequency of the system, let us assume that the clock frequency of the system is equal to 2 megahertz, and I have told that if the clock frequency is of 2 megahertz, then half of the clock frequency is nothing but of the operating frequency of the microprocessor, right? So 2 megahertz the clock frequency, and the operating frequency is of half of it, 1 by 2 is equal to 0.5 microsecond. Now let us see how to find the delay or this count value. Okay, so to calculate the delay, we use the following formula: T delay is equal to T naught plus TL, where T delay is the total delay, T naught is the delay outside the loop, and TL is nothing but of the delay of the loop, right? T naught is the sum of all delays outside the loop. Now let us try to find the delay for the given program, right? We have already chosen a program, move immediate C comma a count value. Our task is to find the or load this count value by means of this calculation. Decrement C, jump on no 0. What this program is going to do is, it is going to be inside this loop until the count value becomes 0. So by means of which we are going to create a delay, right? Until this count becomes 0, it is going to monotonically with inside this loop. Once this loop becomes 0, once this count becomes 0, it is going to come out of the this loop, and it is going to execute rest of the lines in a main program, right? Now already we have seen that move immediate C has 7 T state, decrement C has 4 T state, and jump on 0 loop has 10 or 7 T states. Then we have assumed that the clock frequency is equal to 2 megahertz, and half of the clock frequencies of the clock period, that is equal to 0.5 microseconds. Now let us find the time required to execute this move immediate C. We have seen that it takes 7 T states to complete this move immediate C instruction. So 7 into 0.5, for our chosen example the T is of 0.5, so 7 into 0.5 microseconds, so T naught is equal to 3.5 microseconds. So time delay in the loop is nothing but of this 10 T states plus this 4 T states. So 10 plus 4, 14 T states are nothing but of the time which is being taken by means of the 8085 microprocessor to be inside this loop, right? Until the value becomes 0, what it is going to do? This loop is going to be executed. So for decrement C, it takes 4 T state. In order to jump to this particular loop, what it has to do? It has to read this 2 instruction. Before reading this, it is not going to read this instruction, it is going to read the address as well as the opcode for this instruction. So it is going to take 10 T states for reading the opcode as well as the address which is being here. So 4 plus 10, 14 T states are being required in order to be inside this loop, right? So 14 into 0.5. So 14 into 0.5 into the count value. How long? Until the count value becomes 0. So 14 is nothing but of this 4 plus 10, 14 into T. T is nothing but of the clock period into how many times? Till the count value time. So TL within the loop time is nothing but of 0.5 microseconds, that is T into 14 into the count value is nothing but of the loop T state or loop time. Since we are in need of the count value, we are unaware about it, so 7 into count microseconds, we will be getting point, if we multiply 0.5 into 14, we will be getting 7 into count microseconds, right? So the t state for jump on no zero, the t state for this jump on no zero is 10/7. So we have also have to consider 7 t states for jump on no zero. When loop execute for specified count, and at the last when the condition is false, when the count value becomes 0, what it will do is it will goes to the next state. It won't read this particular address. Once when the um, thing is of once when the count is of 0, it won't jump to this particular address. It will be going for the next address of the program. So at that instant of time, it is out of the loop. When it is out of the loop, it will be taking only 7 t states. So we have to subtract 3 t states from this 10 t states, right? So we have to subtract this 3 t states from this 10 t states. I will repeat it. Once when the program is inside the loop, what happens? It is going to this jump on no zero is going to take 10 t states. When the count value becomes 0, what it will do is it won't go to this address location, and it will again, it is not going to decrement the C register. So as soon as the count value becomes 0, it is going for the next line of the program. When it is going to the next line of the program, at that instant of point, this jump on no zero instruction is going to take only 7 t states. When it is inside the loop, it is going to take 10 t state. When it is out of loop, that is once the loop is being completed, or once the count value becomes 0, what it is going to do is it is going to take only 7 t state. So hence what we have to do is we have to subtract 3 t states from this 10. Okay, and we have to proceed the calculation. So TLA is equal to 3 t states, that is after the loop is being executed, the time is of 3t, that 3 into 0.5, that is equal to 1.5 microseconds. So now total time taken, tt or time delay, is given by tt is equal to t0 plus tl minus tla, right? T0 is nothing but of the move immediate C instructions time taken is nothing but of t0. TL is nothing but of the time which is being taken when it is executing inside the loop, and TLA is nothing but of the time which is taken by means of this jump on no zero instruction when it is coming out of the loop, right? So 3.5 plus, we have already calculated t naught is equal to 3.5 plus, and TL is also being calculated 7 into count minus this 3 into t, it is equal to 1.5 minus 1.5 microseconds, that is equal to 2 plus 7 into the count value. So now if you need delay for 1 millisecond, you assume that we are in need of 1 milliseconds of delay, that is this program have to make a 1 milliseconds of delay. What would be the count value we will be loading in this particular area? That is being calculated now. Suppose if you want if you want 1 milliseconds of delay, or this program have to make a 1 milliseconds of delay, then this tt, total time tt is equal, is being given 1 milliseconds. 1 milliseconds is equal to 2 plus 7 into count of microseconds. We are in need of the count value for this 1 microseconds. So count is equal to 1 milliseconds minus 2 divided by 7, that is equal to 140, right? So if we, this 140 is a decimal number, we have to convert it to hexadecimal value, and that particular hexadecimal number is being loaded over here. Move immediate C comma this 140's hexadecimal value will be loaded here. If we load it, then this program will give us a 1 milliseconds of delay for the operating frequency of how many megahertz? 2 megahertz, right? So the maximum delay which can be created by means of register is to the maximum of 1.8 milliseconds only. That is, we can load the maximum value what we can load in the counterpart is FF. FF is nothing but of the maximum value. Since it is of a 8-bit register, 8085 holds 8-bit value only, the maximum 8-bit value which 8085 microprocessor holds is of FF, and the minimum is of 00. FF is equal to 256, isn't it or not? So 256 in decimal and FF in hexa is nothing but of the maximum count value which we can load, right? So that FF, if we load FF, we can make a delay of 1.8 milliseconds only. Suppose if we are in need of more than that particular time period of delay, then what we can do is we can go for another method. The second method in the so this is nothing but of the second method, time delay using register pair. Instead of using registers, here we are going to make use of register pairs. The time delay can be considerably increased by setting a loop and using a register pair with a 16-bit number. So the maximum 16-bit number what we can use here is of FFFF. Since there we have used registers, we can load a maximum of FF only. Here we are going to make use of a 16-bit register. So the maximum number what we can load is of FFFF. The 16-bit number is decremented by using the instruction DCX, right? We can decrement it, isn't it or not? So however, the instruction DCX does not set the 0 flag, and without the test flag, jump instruction cannot be moved or jumped to a desired condition, right? Additional technique therefore we must be used to set the 0 flag is by means of using OR instruction. So in the previous, what we did is we have checked whether the desired condition is being met or not. We have decremented the count value, and by means of decrementing the count value, what we did, we have checked the 0 flag. Once it becomes 0, the loop comes out. Here, since we are making use of 16-bit register pair for loading the count, and we have to check it by means of decrementing the count value, right? So by means of simply decrementing it, we can't check that flag value because it is a 16-bit number. That 16-bit number, when the flag register does not tell when the 16-bit number becomes 0. So what we are going to do is we are going to add a OR instruction. By means of this OR instruction, the 0 condition is being checked. Okay. We need to consider the things that we cannot check whether the register pair is 0 or not using jump instruction JZ or JNZ. So we use OR instruction to check whether the register pair is 0 or not. So I have written here a program using register pairs LXI D comma a 16-bit count value or 16-bit data. Since here it is of DE register pair, the content of DE register pair are viewed as data only by means of microprocessor. Instead of D, if you put H, then this 16-bit will be a memory location. The microprocessor will be viewing this 16-bit thing as a memory, right? So decrement D, what it will do, this instruction decrement D decreases the DE register pair by 1. The problem in DCX instruction is it does not change the 0 flag. So we cannot use JZ or JNZ instruction. To overcome this problem, we use OR instruction. We do logical OR between this D register and E register, right? So in order to make OR operation, what we did is the E register content is being moved to the accumulator in the second line, right? So to what we are going to do is we do logical OR between D and E register, that is D and A register. If both register contain 0, then only 0 flag will be set, which is the needed condition for us. So the instruction move A comma E, what it will do is it will perform logical OR operation between the content of E and D. One data need to be moved to A register. Here we are moving the content of E register to accumulator. The instruction ORD performs logical OR operation between accumulator with register D. This instruction sets the 0 flags only when the content of D and E are simultaneously 0. The instruction jump on 0 checks whether the 0 flag is set or not. If the 0 flag is set, the flow of program will jump to the given label. Else the flow will jump below the jump on no 0 loop instruction. Right? So again you take that the clock frequency of the system is of 2 megahertz and the clock period is of 0.5 microseconds. Here we have to calculate three time variables T0, TL and TLA. Time to execute LXI comma this 16-bit count is being first calculated. So T0 is equal to 10 T states, right? For LXI comma 16-bit, it is going to take 10 T state, that is opcode fetches of 4 followed by means of 2 read cycles. A read cycle consists of 3 T states, another read cycle consists of another 3 T states. So 6 plus 4, 10 T states are being required for LXID. So 10 into T. So here T is of 0.5. So T0 is equal to 5 microseconds. Next, time to execute this loop. DXD is of 6 T states, right? And move A comma is of 4. ORE takes 4 T state and jump on no 0 takes 10 or 7 T state. We have already discussed about this, right? Next, we will see the time delay in loop TL. That is T into loop of T states into 16-bit count. Here T is equal to 0.5 and the loop in T states are nothing but of 6 T states plus 4 T states plus 4 T states plus 10 T states. So inside the loop, the total T states are of 6 plus 4, 10, 10 plus 4, 14, 14 plus 10, 24 T states are being there. So 0.5 microseconds into 24 into the 16-bit count value is nothing but of the time which is being taken by means of the program to execute within the loop, right? So TL is equal to 12 into 16-bit count microseconds, right? And when it is being coming out of the loop, what we have to do, the jump on no 0 instruction is going to take only 7 T states, so we have to subtract minus 3 T states with the already executed T states. So what we are going to do is TLA is equal to 3 into T 1.5 microseconds. Now total time taken is equal to T0 plus TL minus TLA. So 5 plus, we have already calculated 5, T0 is equal to 5, T0 is equal to 5 plus 12 into 16-bit count minus this 1.5 microseconds. So that is equal to 3.5 plus 12 into 16-bit count value. Suppose if we want to have a 50 milliseconds time delay, we are in need, this program have to create a 50 milliseconds of time delay. We can't make use of the previous program because the previous program which used a register only for calculating the time delay is going to make a maximum delay of 1.8 milliseconds only. So what only we have chosen this kind of register pair for creating the delay, right? Here we are in need of 1.5 microseconds of delay, right? So sorry, we are in need of 50 milliseconds of delay. So 50 milliseconds, TT is equal to 50 milliseconds. So 50 milliseconds equal to 3.5 plus 12 into 16-bit count, right? So we will be getting 16-bit count equal to 5000 minus 3.5 divided by 12, that is equal to 4166 in decimal, which is equivalent to 1046 in hexadecimal. So in the place of the count LXI D comma 16-bit count, if you substitute LXI D comma 1046, then the written program is going to create a delay of 1.5, sorry, it is going to create a delay of 50 milliseconds of delay. So the maximum value that can be loaded in register pair is FFFF. That is what I have told, which is equivalent to 65,535 decimal values. With this value, the maximum delay is 3.5 plus 12 into 65535, that is equal to 7,86,423 microseconds. So 0.78 seconds is nothing but of the maximum delay which can be obtained by means of making use of this register pair, right? This is maximum delay at a system clock frequency of 2 megahertz. It differs with the system clock frequency. For example, if the clock frequency is of 1 megahertz, then the maximum delay will be calculated as 10t plus 24 into 65535 t minus 3t. So we will be getting 1.5 seconds of delay. So the maximum delay at system clock frequency of 1 megahertz is of 1.5 seconds, right? For 2 megahertz it is of 0.78 seconds. So as the system clock frequency changes, what it is going to make? It is going to change the delay value, right? Now the next method to increase the delay is by means of time delay using loop within loop. A multiple loop is used to create a large delay here. We are using loop within a loop, right? So what we are going to do is we are going to move immediately a 8-bit count value inside a register. We know that it takes 70 states, and next what we are going to do is we are going to load another immediate value to a register, and that particular register is being decremented until it becomes 0. It is going to be inside the loop 1. Once this loop becomes 0, what it is going to do is it is going to come out of this loop. As soon as it come out of the loop, what we have written is we have written decrement b. That is, we have already loaded a count value. That value will be decremented until the first value goes to 0. The loop will be executed again, right? So once this loop 1 and loop 2 both become 0, the program comes out of the loop and it will execute the next instruction in the program. So now we are going to find the delay which is being created by means of this loop by means of taking an example. You assume that the clock frequency of the system is of 2 megahertz and the clock period is 0.5 microseconds, right? So now we are going to find the delay which is being created by means of loop 1, right? So total delay t1 is equal to 7t states plus within loop is of 4 plus 10, 14 into this count value 255. FF is being loaded, maximum count is loaded 255 minus 3. That is, once it is being coming out of the loop, the next instruction it is of going to take 3 states, so minus 3t states, and that will be equal to 4t plus 14t into 255, that is equal to 4 into 0.5 plus 14 into 0.5 into 255, that is equal to 1787 microseconds. For loop 2, it is going to take 70 states plus this loop 1 TL1 plus 4t states plus this 10t states into the count value minus 3t states, right? So that will be equal to 4 into 0.5 plus TL1 is 1787 plus 14t states, that is this 4 plus 10, 14 into 0.5 into the count value, right? Move immediate b takes 70 states, so 70, right, plus this loop 1's time taken TL1 plus this 10 plus 4, 14 t states into the count value. So it will be equal to 2 plus 1794 into count value. Suppose if we are in need of 100 milliseconds of time delay, right? So that will be equal to 100 milliseconds equal to 2 plus 1794 into count, right? So we will be getting 56 in decimal value, that is 100 milliseconds minus 2 divided by 1794, that will be equal to 55.74. so we'll be getting 56 as a decimal value. The hexa equivalent of 56 decimal is 38H. If you put a count value of 38H over here, then this program is going to make a delay of 100 milliseconds. So the maximum delay at a count of FFH is 0.45 seconds for the system frequency of 2 megahertz. If it is 3 megahertz, then we will be getting some other maximum delay value for the program. So now it is of assignment time. Try to write a 8085 ALP for a delay of 2 milliseconds, assuming that the operating frequency of microprocessor is 3 megahertz. I have made it as 3 megahertz. We have seen example for 2 megahertz only. So if you change it to 3 megahertz, you try to find the count value for 2 milliseconds, right? And write a program to count continuously from FF to 00H using register C with a delay count between each count and display the number at one of the output port. So I will just give the hint for you. You initialize a register as counter. After initialing it as a counter, decrement that counter value, right? After decrementing that counter value, load the C register with delay count. Right, B register is nothing but of a counter value. Since you have been asked to count from FF to 00, that count value is being loaded in B register. In order to create delay between each count, the C register is being loaded with the delay count value, right? So decrement the delay count. If the delay count is equal to 0, then you go for the count display, right? If it is not equal to 0, you continue with the loop, right? So I have given a flow diagram for this program. You try to write the program for it, right? So next, write a 8085 ALP for a delay of 1 millisecond, assuming that the operating frequency is of 3 megahertz. And also try to write the assignment for the rest of the 3 programs also and submit it in Moodle class.